Hello, everyone. My name is Mel Meng. I'm a support engineer at Innovice. Today, my topic is using AI model for sanitary sewer hydrology. Here is an outline for the presentation. We'll start with a brief introduction of sanitary sewer hydrology and the challenges of the traditional methods. Then we're going to dive in LSTM, and I'll walk you through how I set up a LSTM hydrology model. At last, we'll have the conclusions and discussions. So this picture shows the complexity of the sanitary sewer hydrology. As you can see, when we're taking our shower or flush our toilet, the wastewater will go through the laterals, then all the way into the trunk line in the street. Then from there, the wastewater will flow all the way to the wastewater treatment plant. And as you can see, that is a very long journey, and there are so many places water from outside the pipe can get into the sanitary sewer pipes. From the defects, like the tree roots at the joints, or some of the defects on pipes, on the manholes, or even some connections from catch basins. As you can see, this is a very complicated process, and also it's almost impossible for us to identify all the different sources. So how traditionally we're modeling this process, because modeling this process is important because if you look at the typical sanitary sewer during the dry weather, maybe 50% of the flow is from outside of the pipe. And for some of the system that's very leaky when it rains, the peaking factor can go like 10, 20, or even higher. So it's very important for us to understand this. As you can see from this picture, it shows the typical hydrology. Say we have a flow meter at one of the basin. And you can see at the bottom is the seasonal changes of the groundwater goes up and down. And if we zoom in just to 1 week, as you can see here, typically the groundwater doesn't change too much over 1 week. And on top of that is the wastewater. You can see it shows a very strong diagonal patterns. As you can imagine, usually, we will have more wastewater during the breakfast or dinner time. So that's typical what you see here. And when it rains, as you can see, the red one is the faster response. Usually that is inflow. Maybe you have a directly connected catch basin. That's why it shows immediately when it rains. And also we have the purple part. That's called the infiltration or slow response. Those might be the water coming in through the cracks of your pipe. The water have to work through the soil all the way down there. So that's why it takes a little bit longer. Okay. So usually this is how we develop the sanitary sewer hydrology. So if you look at this, so different from water meters for sanitary sewer, usually we don't have flow meters at every house because the technology is different. It costs a lot more money to do that. So what usually happens is there are flow meter strategically placed at the major branches. So you can see the flow over this whole branch. If you look at the flow meter here, then we'll just extract the hydrology parameters. We'll figure out what the diagonal pattern looks like with that typical wastewater. And then mostly we're using curve fitting techniques to simulate the flow during the wet weather. And as you can see, because we don't really know that much about the sources of these inflow and infiltration, it's mostly a curve fitting technique. That's why I call this a gray box. So after this step, in general, we will have a step 2. So we'll need to average the flow observed here to all the different loadings. So when we wrap the flow through this network, we'll pretty much see similar things. So that's the step 2 called average to the loading nodes. So in this presentation, we're going to focus mainly on step 1, just to replicate the meter hydrology and this flow meter. So to summarize, for the hydrology model to be useful, we need to be able to do the 3 things. The first, we need to be able to calibrate the model. As I have shown, there's very little you can directly measure, directly see where the water is coming from. So we have to look at the data and calibrate the model to match what is observed. And once the model is calibrated, there are 2 major applications. We can do real-time application and planning applications. So those are the main things we need to be able to achieve with a useful hydrology model. So here are some of the major challenges with the traditional methods. The first one is just the cost. Calibrating a model is mostly a manual process. It can take hours to days, depending on the complexity of the model, for just 1 meter. So if you have a system with 50 to 100 flow meters, it can add up very quickly. And the second is accuracy. the traditional hydrology model is based on equations. So if the reality is more complicated than what these equations are describing, and throwing more data at the task won't improve the accuracy of our model. And the last one is for the real-time application. As digital twins are gaining more and more traction, real-time application will be more common. To make real-time application work, we need simpler, faster models that can assimilate real-time data and cheaper to build and maintain. And because of these challenges, that lead us to looking for an alternative. So we're hoping there is a data-driven modeling approach that can automatically learn from the data and improve the accuracy over time so that it can save money and deliver a better model. And that's what leads us to this model called LSTM. So what is LSTM? So before I give you an introduction for LSTM, I'll explain what it does. So as you can see, the problem at hand is we have the rainfall data, and then we need to predict what the flow will look like at the meter. So this is just typical hydraulics modeling problem. And the way this particular LSTM I use solve the problem by doing this. This is a little bit different than how we do it in hydraulics models. So my input is the past 7 days of the rainfall data. And with that data, I only predict one value, a single flow value at this point. So with this model, I can slide this window to the right one time step at a time, and then that will give me a continuous output of the flow. So that's basically what this LSTM model does. So I do want to point out, LSTM model is fairly flexible. You can do many different things. I just happen to choose this particular architecture to solve this problem. And the model I use is based on this blog post, reproducing rainfall runoff modeling using long short-term memory networks. So I use a code referenced in this blog post, and that blog post is based on this research paper. And most of the introduction stuff I listed here are from this paper. So let's take a dive into what LSTM is. So LSTM stands for long short-term memory model. So as it suggests, it can utilize sequences of data. So that's where the long short-term comes from. You can use a longer sequence to predict. So in our problem is we have rainfall data. So this will be the 7 days rainfall data. So each will be a rainfall value for that particular time step. So that's our input. Then we feed that data to 2 layers. The first layer called first recurrent layer, and the second layer called second recurrent layer. And then after that, we'll be going through a dense layer and condense that into a single value for the flow. So you can see the input output, is very straightforward. So the magic is done inside. So what exactly is happening here? So you can see for this layer, each box is a function. You can just think about it as a function. So for example, this one, it takes 2 input and gives out 2 output. It's exact same function, one after another, exact same. Similarly, this one exact same function takes 1 in, 2 in, and 1 out. Each box is the same. So that's how the model is set up. You might find it a little hard to understand, why it's doing it this way. So to help you understand, I'll show you this structure is actually very similar to how we solve differential equations. So here's the example I gave. You can see this is a diagram of groundwater infiltration in InfoWorks Icwmm. So here is a groundwater store. Here's a soil water store, and here's a groundwater store. So you have soil infiltration into the soil store, and then it percolates. Part of it goes into the pipe, part of it goes into the groundwater. I can see this is the pipe. And once you get into the groundwater, part of it goes into the pipe, part of it just got lost into the base flow. And then you can see for the soil store, for the groundwater store, you can just think of those as a function. They take different inputs and give different outputs. You see that it's very similar to this. So maybe this is a soil store, and then this is the groundwater store. And then after one time step, you move to the next time step. You take the new rainfall, the other step. Then you can see moves here. So the similarity between the structure of the differential equations and the LSTM, gives LSTM power. So LSTM is considered the state of the art time series modeling tool. It outperforms most of the traditional modeling tools. Okay, so the magic that really happens for LSTM is how the training works. So the training is where we optimize all the parameters inside of each of the computing units, not too different from like Swim model. You have different parameters to optimize. So here is how it works. So as I have already explained, so we take the input, that's the past 7 days of rainfall. The output is a reading. So we prepare 500. So say that's one batch. I prepare like 500 of these samples, and then I initialize my model with random parameters. And run through that, I got the simulated values. And then there's a loss function. I can compare the observed values with the simulated values. And then I feed that back to this back propagation process. So that's the optimization process to update the weight so that the observed and simulated results are similar. So if you think about that, it's not that different from how we manually cover the model. You see the simulated is higher than the observed, then you tweak some parameters to bring them closer. So essentially, it's the same thing it is doing, but it's on a much larger scale and it's fully automated. So once it goes through this, it's called one iteration. So for me, I usually do 50 to 100 iterations. So after all that, magically we'll have a model that just can predict what it looks like. So that's the basics of the process. Okay, so next I'm going to explain and walk you through the process, how I set up one model to do just that. So here's my experiment setup. So I have the historical rainfall and weather data as an input, and then I use a Icwmm Swim model to generate the flow as output. So that's my source. So I'm trying to replicate the results from a Swim 5 model using a AI model. So that's what I'm doing. So most of the things I tried are mainly on the training side. I didn't touch too much on the architecture of the LSTM model. So one thing I can try is what do I use as input other than rainfall? Can I use past flow or something else? So that's one thing. And the other thing I tried is can I use different events? If I separate a dry weather and a wet weather event, if I train those models differently, then that help. So those are the things I did. And here are the hardware and software I use. So you can see this model is written in Python. Use PyTorch to implement the LSTM model. And I did use Profit to extract the wet weather and the dry weather component. So as you can see on the hardware side, I just use a laptop, and I have a NVIDIA RTX A2000 GPU. That makes a huge difference. So with the GPU, I can usually train my model in a few minutes to 10-20 minutes. It doesn't really take too long, so it's not very intensive on the computing side. Okay, so here are the rainfall and weather data source. Because I'm based in Columbus, Ohio, so I just pick the long-term rainfall and weather data from the airport at Columbus. So the data I use is called Automated Surface Observing Systems. So that's basically all the major airports around the globe. They will transmit weather data every minute. So that data has been around for a very, very long time. So I downloaded the data about for the past 20 years. So that's my source of the rainfall data. And then I used a OpenSwim example model that has groundwater, runoff, and infiltration all turned on. So I can simulate the full hydrology. In addition to these, I also added the dry weather flow to that model. So here is a sample of the model output. As you can see, the top is the model flow, and the other are the different components. So you can see the dry weather flow. So you can see the general patterns, and the orange is the groundwater. As you can see, there's some seasonal changes, and also there's runoff when it rains. So also soil infiltration is also simulated here. You can see it goes up and down in this graph. Okay, so here is LSTM and training parameters. So for me, I use a sequence of 2 weeks input data. So in the previous slide, I showed like you use 1 week. So I didn't change this too much. It's kind of a little bit random. So I tried different lookbacks, and if I do anything beyond 2 weeks, my video card doesn't have enough memory. So I kind of just say, hey, I'll use as much as I can. And it gives me good results. And the batch size, I use 500 samples. And for the learning rate, I switch between 0.1 and 0.01, depending on how well the model is learning. And there are 20 hidden units. So I did very little changes to the architecture. Most of the things I changed are on the training side. Okay. So before I dive into the full model with all hydrology, I started with something really simple. It's just a RTK model. As you can see, very simple RTK parameters, and I did add some initial abstraction parameters. And then you can see here are the results. So I trained the data the model on the data from 2020, 2021. And then, I tested the results. So the model haven't seen the data in 2022. So this is 2022 data. It looks pretty good. Other than this one, everything else looks very close. And the next, I try to see, okay, what if I use this model to try some of the design storms? And as you can see, for the 1 year, 2 year, 5 year, 10 year, SDF type 224 storms, the orange is the simulated results. So it's much lower than the observed flow. So definitely that is it's a limitation, but it's not a surprise. As you can see, if we draw this line around 0.03, there are only like 3 events we have seen in the training data. So that's a major limitation of the LSTM is if it hasn't seen enough of the samples in the past, it cannot correctly interpolate that for the data. So that's one of the major limitations. We'll talk a little bit how we can address this limitation in a later slide. Okay, so I was actually quite excited after doing that first test. So then I feed my model with all the hydrology parameters turned on, but I was quite disappointed. As you can see, the blue line is the observed data, and the orange line is the AI interpreted the simulated results. I mean, it's basically a flat line. The model failed to learn at all from this. The results is really bad. So how can we improve this? And I tried 3 different things. So the first is just I remember in the old days when I do model calibration, what did I do? I first separate all the different flow components: driver of the flow, groundwater infiltration, and then runoff. So maybe that also works for AI models. So let's try to separate these different components. And the second is, I'm quite excited is, AI model is very good at data simulation. So basically, I can feed the flow from the past and use that to, predict what the flow will look like in the future. This will be something almost impossible to do with typical hydraulics models. You have to build specific special engines to be able to do this. But for AI, it's super easy to do. And the last one is, what about events, right? So when we calibrate models, traditional models, we calibrate model during wet weather events, during dry weather events. Maybe the same technique can also work. So let's see, how we can apply all these techniques. So how can we separate the dry weather flow component? So you can do this in Excel. You don't have to use this library, but I found it's easier to do it this way. So I'm using the Facebook Profit. So that's a time series forecasting library. So it's very easy to use. You pick a very good dry weather period of time, and you train it with Profit, and Profit will give you the downward pattern, and then the daily pattern over the week, and then also give you a long-term trend. So it's kind of tells you what the groundwater will look like. So if we combine the daily pattern and downward pattern, we will get a very good dry weather flow. So my idea is, in addition to the rainfall data we feed into the model, let's feed the downward patterns or the dry weather flow as the second input. Well, probably that will help. So that's the first thing we can add. So the next thing we can add the data assimilation. So like I said, this is a killer application for a real-time application. As you can see, the idea is very simple. So in order to predict the flow here, what if I tell the AI model what happened just a day before and for the past 7 days or 14 days, whatever that sequence is? Will that help? Help. It looks very similar from last day to today. So one thing I want to point out, if you have real-time application, you have very good real-time network, you can get data within an hour. You can just shift that by 1 hour. That will work even better than this. Okay, so what about events? So let's take a look. So these are rain events, and you have dry weather events. So let's take a look for the rain event first. So as you can see, when it rains, there are 2 processes working at the same time. You have the runoff, and you have the groundwater. So my feeling is probably it's too complicated for the AI to learn. So maybe we should separate the groundwater component from the runoff. That way we can make it easier for the AI model to learn. So this is one thought. We keep it. So another thing, I want to point out is actually for groundwater, it is much better to train the groundwater during the dry weather event. The reason is once it rains, it's very hard to separate this. You don't know when is what is a runoff, what is storm, the groundwater infiltration. And also just recall that how we actually do this in the AI model. For each of this point, we look back for 7 days or 14 days, right? So although we're not particularly training the data during the rain event, we're not ignoring the rainfall from these events. They're still used for each of these. So that's the concept behind it. So, how we can train only on dry days, but, also we're not actually missing out the rain events for the groundwater. So those are the last idea, we can try to improve the results. So now let's see, after applying all these different techniques, how does it work? Okay, let's look at the first one. So the first one is I just added the dry weather flow. I calculated from profit. Let's see how that works. You can see, remember, the first try I had, these are basically flight lines, just all the way through. So this is a huge improvement from that. You can start to see downward patterns here and there, but you will notice the groundwater is not well, simulated. You don't see the up and downs here. So let's look at the picture down here. So for this one, after adding the dry weather flow, I added a third input. That's the past flow like from a day before. And you can see here, definitely is a huge improvement on the groundwater during the dry weather conditions. But still, when it rains during the rain event, it's all over the place. It doesn't look that great. Okay, but at least you can see adding dry weather flow solve the downward pattern problem, and adding the past flow give us a much better match for the groundwater infiltration up and downs. So let's see what else can we improve? As we said, maybe we should only train on the dry weather events, because that is more accurate for the groundwater infiltration. So when you compare those two, so this one is we train on the dry events. It doesn't look that different from this picture, but if we zoom in, as you can see, there's a huge improvement. You can see how well the dry weather during the dry weather conditions, it matches the up and downs of the groundwater infiltration. So training on the dry events helps a lot in this case. And that leads us to the last piece of the puzzle. So what happens when it rains? With the current format, it's, I have to say it's kind of bad. Like this guy here, they're very wrong. And you can see around here and there, it doesn't look that great. So how can we improve? So as I explained, it might be just too complicated when you have groundwater infiltration, when you have the runoff. It's just too complicated for the AI to learn from it. So is there a way we can separate the groundwater infiltration and the runoff? And here is one thing I tried. It seems to work pretty well. So the assumption is, as we have seen, when it rains, the groundwater doesn't change that much. It usually is like a day or two delay. So usually, after it rains, probably we'll see somewhere here start to see, the real impact for this rainfall. So because of that, so what I did was let's remove the rainfall here and keep everything else. And then we run the AI model. And then this is the orange line here. So you can see this kind of represents what the actual groundwater might look like. So the nice thing about LSTM is I don't need this line to be perfect. LSTM is very good just to take hints or some guesses. It doesn't need to be perfect. And then, LSTM can incorporate this knowledge and help to improve the interpolation. So I have high hope that this will help. So let's see, how that works. So as you can see, so this is the last model we had, and it has a lot of trouble predicting the wet weather event. You can see the misses here, all the big ones don't look that great. So after I train the events using the rain events, only during the rain events, and replace the dry weather flow pattern with the AI-generated groundwater inflow, and this is what we got. You can see, all the rainfall events, looks much better than before. So it's a huge improvement. And if we zoom in, you can see, this is much better match than before. However, I did notice, you can see, if you look at that during the dry weather events, the match is not as good. That's kind of expected because we train only on the rain events. So I can see there are a lot of interesting work I can continue on this to reconcile those two models and make the prediction better. But for me, I'm very happy with this last model I built. It looks pretty good. Okay. So that's kind of like most of the experiments I did. But before we leave, I just want to touch back a little bit on the interpolation. So remember, for my RTK model, there are a lot of problems here to interpolate the results to something that we haven't seen before. So there are ways, for the AI model to overcome this, and I think so. We can go back to the existing hydrology theories to help us. So one thing, I feel like has a chance is the unit hydrograph theory. So according to the unit hydrograph theory, so once the basin is fully activated, the runoff response is fixed, regardless of the total amount of rainfall. So basically what that says is, once you started to have water flowing freely on your basin, every time you add a unit rainfall, you will have a response looks like this curve. As you can see, so this is a SCS unit hydrograph method. So that's what that theory tells you. So can we use this to improve the results? I believe so. So here is just a concept. So as you can see, if this gray rainfall is a calibrated rainfall and flow, and then we give you a response of this blue line. So we're confident this is accurate. And now what we need to do is we need to run a design storm with a five-year storm that has a huge peak in the middle. And how can we do this? And we know if we just run the model as is, it will be wrong because the model had never seen anything higher than probably like this, and it won't get the right results. However, we can try to apply the unit hydrograph concept. So what if we just add a very small increase to this rainfall at this point? We run the model, and then we see the new hydrograph will look like follow this yellow line. So as explained by the previous slide, the difference between the yellow line and the blue line is the unit hydrograph. So say if this rate increase for the 5-year storm is 10 times of this, then we just need to time this area by 10, add that up, and that will give us what the 5-year storm will look like. So that's just one idea I would like to share to overcome the AI limitations. Okay. At the end, I would like to share some conclusions and discussions. So as you can see, we successfully trained a LSTM model to reproduce the results of a Icwmm 5 model with dry weather, runoff, groundwater, and infiltration flows. And with a fixed LSTM model architecture, we explored several data engineering and training techniques to improve the AI model accuracy. The traditional approach of modeling individual flow components worked well in our experiments. And since most part of the LSTM modeling process can be automated, AI model has the potential to dramatically reduce the cost of calibrating a central zero model, hydrology model. So I'm very excited about the potential of this technology. So next steps. Definitely I would like to apply the same workflow on real world data to see how well that works. And also I would like to continue to research on how we can interpret model results for larger design storms. And at last, I would like to build a hybrid model with AI hydrology and Icwmm hydraulics. And I think the key will be to use AI to average the meter hydrology to the loading nodes. And that will give us a full solution to augment the current technologies. And that is my presentation, and thank you very much.